For billions of years, the sun has been the ultimate engine of life. A celestial furnace burning with an intensity that defies human comprehension and scale. Our modern civilization is built upon the consumption of vast amounts of energy, lighting up our cities and powering the technologies that define our current daily lives. But this progress comes at a heavy price, as our reliance on fossil fuels pushes the planet toward a breaking point of catastrophic climate change and instability. The ice is melting, the seas are rising, and the window to save our common home is closing faster than we ever imagined possible for humanity. From the first spark of fire to the massive coal plants of today, our quest for power has shaped history, yet we remain bound to finite resources. Now, we are on the verge of a new era, seeking to replicate the very power of the stars right here on the surface of our planet. In laboratories across the globe, the brightest minds are working tirelessly to unlock the secrets of nuclear fusion, the holy grail of clean and sustainable energy. Imagine a world where energy is clean, safe, and practically infinite, freeing humanity from the chains of pollution and the constant threat of resource depletion. While renewables are essential, we need a massive, steady source of baseload power to truly transform our global energy landscape for the long-term survival of all. The fuel we need is found in common seawater, providing a source of power that could last for millions of years without harming our fragile environment. The journey is difficult.
Copy. Descending.
But the reward is nothing less than the survival of our species and the preservation of the only home we have ever known. To understand the future, we must look at the atomic scale, where deuterium and tritium isotopes hold the key to an incredible release of pure energy. Normally, these atoms repel each other, but under extreme conditions of heat and pressure, they can be forced to overcome their natural resistance and collide. This is nuclear fusion, the process where two light nuclei merge into a single heavier nucleus, releasing a staggering amount of energy in the process. The efficiency is breathtaking. Just 1 gram of fusion fuel can produce as much energy as 8 tons of oil or coal without the carbon emissions. Unlike traditional nuclear fission, which splits heavy atoms and creates long-lived radioactive waste, fusion is inherently safer and produces no long-term radioactive burden. Inside the sun, the massive force of gravity does the work, crushing hydrogen atoms together at its core to create the light and heat we feel. On Earth, we lack that immense gravity. So we must compensate by creating temperatures 10 times hotter than the core of the sun itself to succeed. At these extreme temperatures, matter enters a fourth state called plasma, a chaotic soup of charged particles that is incredibly difficult to control and contain. Because plasma consists of charged particles, we can use powerful magnetic fields to manipulate its movement and keep it away from the reactor's physical walls. The energy released during fusion is carried away by neutrons, which can be captured to heat water, create steam, and ultimately generate clean, carbon-free electricity. Deuterium is easily extracted from seawater, making the fuel for fusion virtually inexhaustible and accessible to any nation with access to the world's vast oceans. Tritium, though rarer, can be bred within the reactor itself from lithium, another abundant element found in the Earth's crust and in our brine deposits. And every aspect of this process requires absolute precision, pushing the boundaries of our understanding of physics and material science to their absolute limits today. The clock is ticking for our planet, making the mastery of fusion not just a scientific goal, but a moral imperative for the future of humanity. We are learning to build a star on Earth, a task that represents the greatest technological challenge our species has ever dared to undertake in history. Enter the Tokamak, a Russian-designed marvel that has become the world's leading concept for achieving controlled nuclear fusion in a laboratory setting. Its name is an acronym for a toroidal chamber with magnetic coils, designed to trap the superhot plasma within a powerful, invisible magnetic cage. These magnets are cooled to near absolute zero, allowing them to carry the massive currents needed to generate fields strong enough to squeeze the plasma. Within this donut-shaped vacuum, the plasma is heated to 150 million degrees Celsius, and a temperature so high that no physical material could ever contain it. The engineering required is staggering, with components weighing hundreds of tons that must be aligned with the precision of a fraction of a millimeter. Sophisticated sensors monitor every microsecond of the reaction, providing the data needed to keep the unstable plasma from touching the reactor's delicate walls. The magnetic field acts as a virtual container, keeping the sun-hot plasma suspended in the center of the chamber, safely away from any solid surface. ITER, the International Thermonuclear Experimental Reactor, is the world's largest tokamak, a collaboration involving 35 nations working together for a common goal. The power required to start the reaction is enormous, but the goal is to reach a point where the fusion process becomes self-sustaining and productive. Every experiment brings us closer to mastering the delicate balance of pressure, temperature, and time needed to achieve a net energy gain from fusion. This heat will eventually be used to create the electricity that powers our homes, businesses, and the entire infrastructure of our future global civilization. We are effectively building a bottle to hold a star, a feat of engineering that was once thought to be completely impossible for humans. Materials like tungsten are used because of their incredibly high melting points, yet even they must be protected from the direct heat of the plasma. It is the most complex machine ever built by humanity, representing the pinnacle of our collective scientific knowledge and our most ambitious engineering dreams. As the magnets hum and the plasma swirls, we are witnessing the dawn of a new age, where the power of the stars is finally ours. This is not just one nation's project. It is a global race, with major research hubs spanning from the fields of France to the labs of China. In the United Kingdom, the Joint European Torus, or JET, has recently set world records for fusion energy production, proving that the concept truly works. In America, the National Ignition Facility uses a different approach, firing the world's most powerful lasers at a tiny fuel pellet to achieve ignition. In 2022, they achieved a historic breakthrough. For the first time, a fusion reaction produced more energy than the laser light used to start it. China's East Reactor is pushing the limits of duration, holding super-hot plasma for hundreds of seconds, a critical step toward continuous, stable power plant operation. South Korea's K-Star, known as the Korean Sun, has achieved record-breaking plasma temperatures, maintaining over 100 million degrees for significant periods of time during tests. While there is competition, there is also unprecedented cooperation, as nations realize that the success of fusion benefits all of humanity, regardless of borders. The progress has been exponential, with every decade bringing us orders of magnitude closer to the goal of a commercial fusion power plant on the grid. We are no longer asking if fusion is possible, but when it will be ready to transform our energy markets and save our warming climate. These milestones are the result of decades of persistence, built on the work of thousands of researchers who dared to dream of a better future. Fusion won't just power our homes. It could be the key to deep space exploration, providing the massive energy needed for long-distance interstellar travel. The race is heating up, with private companies now joining the effort, bringing new ideas and rapid investment to accelerate the timeline to commercialization. Each breakthrough, no matter how small, it is a victory for science and a step toward a world where energy scarcity is a thing of the past. The generation being born today may be the first to live in a world where energy is truly clean, safe, and available to everyone. The finish line is in sight, and the momentum is unstoppable as we move toward the final stages of this historic global quest for power. The road ahead is still fraught with challenges, primarily the astronomical costs of building these massive machines and the materials needed to survive. We need materials that can withstand the constant bombardment of high-energy neutrons and the intense heat of the plasma for years without failing or breaking. Maintaining the stability of the plasma for long periods is another hurdle, as any small fluctuation can cause the reaction to stop instantly and safely. Despite these obstacles, a new wave of private startups is emerging, promising smaller, cheaper reactors that can be brought to market much faster than expected. The goal is to modularize the technology, making it possible to deploy fusion power wherever it is needed, from remote villages to large industrial centers. Fusion offers a way to decarbonize industries that are currently difficult to electrify, providing the high-grade heat needed for making steel, cement, and chemicals. With cheap and abundant energy, we could desalinate seawater on a massive scale, turning deserts into fertile land and solving the world's water crisis. The promise of fusion is a world of abundance, where the cost of energy no longer limits our ability to solve the world's most pressing problems. We are moving from the era of scientific exploration to the era of commercial engineering, where the focus is on reliability, cost, and mass production. By the middle of this century, we hope to see the first commercial fusion power plants feeding energy into the grid, marking a true turning point. The hurdles are high, but the collective will of the global community is stronger, driven by the knowledge that this is our best hope for survival. We are no longer just dreaming. We are building the foundation for a future that will be powered by the very same energy as the stars. The transition will be challenging, but the result will be a planet that is cleaner, safer, and more prosperous for every living thing upon it. As we look back at our home from the stars, we realize that our destiny has always been linked to the energy that powers the entire universe. The sun in the sky gave us life, and the sun we build on Earth will give us a future, free from the shadows of pollution. We have finally learned to harness the fire of the gods, turning a dream of the ages into a reality that will sustain us forever. Thus, this is more than just a technological triumph. It is a testament to what humanity can achieve when we work together for a common, noble purpose. The dawn of the fusion age is here, and with it, a new chapter in the human story begins. One of infinite energy and endless possibility. Let us move forward together toward a brighter, cleaner tomorrow, powered by the eternal light of the stars that we have brought down to Earth.